Okay, does anyone have any questions on the written homework or the Wiley homework? Written homework will be due this Friday, so 4.8 to 6.2. All right, so last time we were talking about 6.1, and we've only done examples with respect to the x-axis. So we're integrating the top function minus the bottom function with respect to x, so our functions need to be functions of x, on our x bounds. So we did an example. No, we didn't quite get to this example. So we were first looking at this example from 0 to 2. So let's pull that up. Let's see if I have that here. We left off with that we were going to start this example, right? So let me just write that here. So part A was to find the area between x equals 0 and x equals 2 of this function. So go ahead and graph this. We have y equals x squared, and then we have this line and this line is y equals x plus 6. Right, so this point would be 0, 6, various points that we know. We're going to integrate from 0 to 2, so if I plug in 2, this point would be 2, 4, this point would be 2, 8. So I want to find the area between these two curves on this interval. Since I'm integrating with respect to the x-axis from 0 to 2, I'm taking slices on the x-axis, right? So I take my top function minus my bottom function to find the area of that slice, and then, or that slab. So it's only in one dimension, a flat surface, it's just a rectangle. And I'm going to add that up from 0 to 2. If I do the summation notation, and I can turn that into an integral, I have dx. The dx tells me I'm integrating along the x-axis. That's going to be important when we look at examples where we look at dy. We're integrating along the y-axis.
Can you get 2, 8, 2, 4?
So if I plug in 2 to this function, I get 8. If I plug in 2 to this function, I get 4. You really don't need those points. I just, to show you, eventually we're going to find more points. So this area is going to be the integral from 0 to 2 of my top function with respect to x, or in terms of x. So that's x plus 6 minus the bottom function as a function of x, x squared dx. Right? I take my top function as a function of x minus my bottom function as a function of x. dx bounds on x, right? So there's a lot of repetition going on here with x, dx, bounds on x. I'm integrating with respect to x. My function needs to be a function of x, and I have this dx. We're going to look at an example where we integrate in terms of y. Your function needs to be in terms of y, and you're going to look on your y bound. So at this point, you should feel comfortable evaluating this integral, right? So this is going to be x squared over 2 plus 6x minus x cubed over 3. Plug in 2 minus plug in 0. So I have 2 squared over 2.
We're supposed to add the c or not. I don't understand.
There's no plus c when definite integrals. We make it 0. But if it's if there's an indefinite integral, means I want to find all antiderivatives. If there's not a bounds, you have plus c.
Okay.
But here I could say plus c, but then I'm going to subtract c anyway, so it doesn't matter. So then this would be 6 times 2 minus 2 cubed over 3 minus 0. right? When I plug in 0, I get 0. Be very careful. If you plug in 0 to a sinusoidal function, it's not always 0. Cosine of 0 is 1. So you can't just assume you're going to plug in 0 and always get 0. But a polynomial, it's safe to say that. So what do we have here? 2 plus 12 minus 8 over 3. What do I get? 34 over 3. Would everyone agree with that? So really in 6.1 and 6.2, it's the setup of the integral that you really have to make sure you have correct. And on this next exam, I'm going to test you on 6.1 and 6.2. It will probably be a setup, but do not evaluate. I'm going to say, can you set it up correctly? I'll ask you, can you evaluate an integral? But then to give you more time, to give you more problems to test you on, it might just be set up, but do not evaluate. So this is what I'm wanting. And then I'll test you individually if you can evaluate an integral that's already set up. Because if you don't set it up correctly, you're going to waste your time because there's no chance that you're going to get the right area. So part B was just between the two curves. Between y equals x squared and y equals x plus 6. So graphing this line, and then I have this equation. So how am I going to find the x-intercepts, or not x-intercepts, the x values in which my functions intersect each other? Yeah, I said these two equations equal to each other. So when does x squared equal x plus 6? Well, when x squared minus x minus 6 equals 0. So when x minus 3 times x plus 2 equals 0. So x equals minus 2 or 3. So this is at x equals minus 2, and this is at x equals 3. So to find this area, the nice thing here is all my slices, my top function minus my bottom function, the same top function minus the same bottom function, right? So I don't have to split this up into two intervals, right? If I went from minus 2 to 5, then from 3 to 5, I would have to separate that and have the top function be x squared and the bottom function be the line. Question?
How do you know that when it gives you negative infinity, how do you know you're trying to find the area between?
The way they won't really say negative infinity to infinity, they'll say find the area bounded between the two curves. So this area would not be between the two curves, it would be this area. Okay. So it will be a little more straightforward. If I said find the area between minus 2 and 5, then you would have a cutoff. So you would then say, okay, I can find this area plus from 3 to 5, which would then have its own shaded area. So this area is going to be the integral from minus 2 to 3 of x plus 6 minus x squared dx. And if I go through and do the calculations, it turns out we get, your book goes through and does this, so let's pull this up. They go through, plug in the upper bound minus the lower bound, they get 125 divided by 6. But I trust once you guys set this up, you can integrate it. So on the next exam, I'm going to test you on set up, but do not evaluate type integral here. So you're going to have to draw the picture, so that'll be worth some points. You're going to have to find your own intercepts, and then you're going to have to integrate along the x-axis or potentially along the y-axis, and we're going to do an example of that. Amanda, you have a question?
I was just
Okay. Anyone else have a question?
So since drawing the pictures is where I have the most trouble. Like I don't know how to visualize what the equation gives me. I can do the equation step by step, just kind of systematically. But drawing the picture.
So anything with like a quadratic shifted up or down or left or right, you should be comfortable drawing, right? X squared plus 5 means that's x squared, I'm shifting that up 5 units. X squared minus 5, I shift it down 5 units from the origin. If I have x minus 5 squared, that means I shift it to the right 5 units. So something with a quadratic you'll probably have, and something with a line. So find the y-intercept and find the slope. And it doesn't have to be perfect. You can just kind of rough draw it. Another thing I've always seen on the final exam or on this exam 4 is an e to the x function. So where does, e to the x?
You have to draw e to the x?
Yes.
Okay.
Or like e to the x in some line. Y equals x. Find the area bounded between 0 and 1.
So is this section in the book going to have some, I guess, good examples where you can practice?
Yeah, you're going to have some pretty straightforward. I mean, this one, something like this I've seen come up in the past.
Okay.
Sometimes they give you the graph. And in that case, setting it up and evaluating it is where you need to go through. Question?
Are we always going to set them equal to 0 or to each other?
If you want to find where they intersect, if you want to say the area of the curve, the area bounded by these two curves, you would set them equal to each other to find the x value in which they equal each other. But the previous example, we didn't do that. We only wanted this shaded region, which is from 0 to 2. So I'm only integrating 0 to 2 of the top function minus the bottom function with respect to x.
Is that usually where the bound's going to be? Is they'll tell us x equals 0?
Mm-hmm. So if they give you bounds, it's a little easier. You just have to make sure that your top function is always the top function in that interval, and the bottom function is always the bottom function in the interval. So let's do one more example of this where the bounds are a little different.
That's why you subtracted x squared, because
The x squared is below. This is x squared, yeah, the line on that whole interval. But let's say we wanted to say part C, and let's say we want to find the area between, let's say, x equals 0 and x equals 5. Let's just say we're going to set it up, not actually evaluate it. So if I have this quadratic, and then I have this line, so from 0 to 5, well, this is going to go up a little bit more. So 5 squared is 25. So this is 5 comma 25. And this point would be 5 comma 5. No, 5 comma, what was the line? 6 plus 5, so 11. So we'd still need to find this point of intersection, which we did, and we know that's going to be 3. But if I want to find the area bounded by these two curves on this interval, I'm going to have to break this interval up into 2 separate intervals, because my top function here, this is y equals x plus 6. This is y equals x squared. From 0 to 3, my top function is the line minus my bottom function, which is the quadratic. But from 3 to 5, my top function is the quadratic, my bottom function is the line, right? You guys see that? So this area is going to be from 0 to 3 of x plus 6 minus x squared dx plus from 3 to 5 of x squared minus x plus 6 dx. The parentheses is very important there. Question?
This is from the previous one, that part.
Yes?
When you go to plug in the x, would you plug in 5 since that's the distance between the negative 2 and 3?
No.
Remember what value you plug?
Here, you'd find the antiderivative,
Yeah.
and you'd plug in 3 minus a negative 2.
Okay.
right? You just use the fundamental theorem of calculus. This is going to be f of 3 minus f of minus 2.
So you plug that, like, the 3 into the equation minus -2 into the equation.
The antiderivative.
Anti-
So then you have to integrate this before you can plug it in. Yeah, and we already did that here, right? It's the same function. So then I'm going to plug in, everywhere I have a 2, I'm going to plug in a 3, and everywhere I have a 0, I'm going to plug in a minus 2. And you're going to get that area. Make sense? Okay, so does everyone understand the setup here?
I don't get why you just got a 3 and all of a sudden it goes up like that.
So the graph of a quadratic, make this a little bit more, this is a quadratic, right? All the points satisfy the equation x equals y squared. This is a line. This line is y equals x plus 6. Y equals x plus 6, right? So from 0 to 3, pretend like this is a line. Not much better. From 0 to 3, this is the top function. This is the bottom function.
Where are you getting 3 from?
This 3 is this intersection when this equation equals this equation. If I plug in 3, I get 9 from this equation. If I plug in 3 here, I get 9. This is comma 3, comma 9. If I plug any number larger than 3 and I square it, that's going to be larger than if I just add 6. 1 plus 6, so this is 1 comma 7. This is 1 comma 1. 1 squared is 1. 1 plus 6 is 7. These points. These equations equal each other when x equals 3. We said those equal to each other, right? So from here, this is just a line, so I know it looks like this. This is a quadratic. It's going to go up like this. So if I want to integrate from 0 to 5, then I'm also trying to find this area, which would be the top function minus the bottom function from the interval from 3 to 5. You have to be able to be comfortable with graphing lines and quadratics. If you're not, that's going to be tricky to visualize. Question?
You don't care about that one.
No, I don't.
Okay.
I just wanted to show you where I'm getting these collection of points.
Okay.
Right. So at this point, I plug in 3 to this equation, I get 9. I plug in 3 to this equation, I get 9. That's where they intersect. But yeah, this is just a collection of points that follows this equation that's saying my y-intercept is at 6 and I have a slope of 1. So 1, 7, 2, 8. These are all points on this. But yeah, I don't need to know those points to be able to do this problem.
And the reason you flip it is just because after that point, the x squared becomes greater than
Yes.
the x
Line.
plus 6.
Yes.
Okay.
So if I wanted to take slices, I take the top function minus the bottom function, and
Mhm.
it changes at this point. This is the top function here.
Yep.
Make sense? So let's look at,
Can you explain the setup of the area?
well, because the top function from 0 to 3, this is the top. And then from 3 to 5, this is the top. So you have to break up your area in which your functions are changing.
And you always add like 2 together.
You always add the two together. Question?
So in order to get that 3, we did what we did up there where they were equal to 0. And
Yeah.
you know it's the 3 and not the -2 because it's on the...
That side, yeah. In that interval from 0 to 5, 3 is included, minus 2 is
Okay.
not. Yeah. Any questions on that? So things to be comfortable drawing x squared or the square root of x. I've seen that come up before. If I have something like x squared, this is y equals x squared. This is y equals the square root of x. And then asked to find this area. Well, if I take the square root of 1, I get 1. If I square 1, I get 1. So this point is 1 comma 1. And this point is 0 comma 0. So then the top function minus the bottom function, which is a little bit weird to think that square root of fraction is larger than squaring the fraction. There's a, you ever heard of the square root club? Where your GPA is actually larger when you take the square root of it? Not a good club to be in. But a lot of times students really struggle on this because they're thinking, if I square something, that's larger than if I square root it. That's not true between 0 and 1. 0 and 1, the square root is larger than squaring it. Right? So just, a quick illustration, if I have 0.5 and I take the square root of that, that's 0.7. It's not a good club to be in, like I said before. And then if I take 0.5 and square it, it's 0.25. 0.25 is less than 0.7. So if you get used to the concepts of graphing the square root versus x squared, because a lot of times students really struggle with that concept, they don't think they intersect. Like I've seen students draw this before like this, where they say this is y equals x squared and this is y equals the square root of x, and then try to do something funky. So hopefully I'll expose you to everything that would potentially be on the final exam, graphing-wise.
As far as the instructions for a problem like that, it would say find the area between them so you
These two
should know
curves.
that they would intersect.
I know, yes.
Okay.
So find the area between these two curves.
Okay.
It might not give you an interval. They might say from 0 to 1.
Okay.
Question?
I know our quiz for chapter 6 is on Wiley.
Yes.
Will there be like graphing and stuff?
There won't be where you have to graph it and show me the graph, but it might be where you have to graph it to find the area.
Okay.
So let's look at some problems from 6-1. Let's just look at it from the homework perspective. So they'll give you some of these graphs, but I would expect you to be able to graph any one of these, right? This is a quadratic shifted up one. This is a line y equals x. And then it gave you from -1 to 2. Y equals the square root of x. Y equals 1/4 x. That tells you you have a slope of -1/4. So it's a line and then encompassing this. It's going to be the top function minus the bottom functions on the interval of x. So the next couple examples, and we're going to look at number 3. And we're going to look at the number 3 one on Wiley. This is very similar. If I wanted to integrate this along the x-axis, I'm going to have to divide it up into 2 regions, which is not going to be very computationally. It's going to take quite a bit more time. So I could say I'm going to slice this with respect to the y-axis. So my bounds are going to be on the y-axis from, in this case, 1 to 2, and I'm going to take my outside function minus my inside function, right? So let's look at writing this up in general. So I'm going to show you how you can find the area of a curve with respect to x and an area of a curve with respect to y. So let's say I have a function. So I'm going to name this function x equals f of y, or y equals g of x. Depending on what you're given, right? I could say x equals y squared, or I could say y equals the square root of x, just as an example. So here this is saying I have a function of y, or I have a function of x. I can name these two different things. You can always solve for one in terms of the other. And let's say this function is x equals h of y, or y equals z of x. Now you're most familiar with these two approaches. Y is a function of x. But you can do the exact same thing as x is a function of y. And it's not going to change your area. So let's look at the area between these two curves. Let's name this point A, comma B, and let's name this point C, comma D. So if I want to find this area, I can take slices with respect to the x-axis, but my functions need to be functions of x. Right? So if I want to find this area and I take slices with respect to the x-axis, the area is going to be the integral. What are my bounds on x? A to c. Of my top function in terms of x, so that's going to be g of x, minus my bottom function in terms of x, which would be z of x, dx. Right? You want to emphasize your functions as functions of x, dx, your bounds on x. But this area is going to be the exact same thing if I integrate along the y-axis. So what are my bounds on y? B to d, very good. B to d. And I'm going to take the outside function, so I'm taking these slices in terms of y, so this would be delta y, this slice would be delta x. So integrating my outside function in terms of y, which would be h of y, minus f of y, dy. In some cases, it's easy enough to do in terms of x and easy enough to do in terms of y. In most cases, one will be easier than the other. But you're always going to be able to potentially break up an interval in enough subintervals to integrate those subintervals in terms of x or in terms of y.
So at that point, CD is whenever, so like before CD, the x equals hy is on the outside or further away. So you would
Correct.
take that minus the top one, but at that other point you'd flip them, right?
Correct, if you wanted to go beyond that.
Okay.
You always take the outside function minus the inside function. So if I go here, this becomes the outside function and this becomes the inside function. So the same thing with x, right? From here, this becomes top function minus the bottom function, but at this point, this becomes the top function and that becomes the bottom function. So let's look at an example in Wiley that's integrating along the y-axis. Question?
Outside, like the right.
Yeah, the rightmost function. So this is basically larger in terms of x. This is larger in terms of y. So you always kind of take the larger function minus the smaller function. Okay, so let's look at, this is Wiley. Assignment. Six one. Let's go to your guys' section. So 6-1. So let's look at this graph. So you notice I could split this up and integrate in terms of the x-axis, but I'm going to have to find this point of intersection and integrate from this point to this point, plus this point to this point. My top function remains the same, but my bottom function switches. So I'm going to set it up in terms of the y-axis and integrate it. Then I'm going to set it up in terms of the x-axis and show you it's the same. The answer is the same. So let's graph this. This is number 3. So I have x equals 125 divided by y squared, and y equals x. Or x equals y. Then we get this point 10, and this point here is 10. So this is what I have here. And I want to find this area. So you can kind of see they've set this up for you to integrate along the y-axis by giving you functions of y instead of functions of x. So if I take slices, I'm going to have dy's. So my functions need to be functions of y. So what are going to be my bounds of integration on the y-axis? This point to 10, right? So how am I going to go about finding this point? Yeah, so if I set these functions equal to each other in terms of y, I get my y point. So it turns out, when does y equal 125 divided by y squared? So when does y cubed equal 125? Y equals the cube root of 125, which is 5. It tells me my y is 5. Turns out x equals y, so x is also 5. So this point is 5, 5.
So that's finding your bottom bound, your lower bound.
Yes, so I'm integrating with respect to y, right? So my area is going to be from 5 to 10. Right, does everyone see that? So I'm integrating with respect to y from 5 to 10. What is my outside function?
Y equals X.
But I want it just in terms of y.
So Y.
Y. Minus my inside function. Yeah, so if I have 125, I'm going to write this as y to the minus 2 dy. Is everyone convinced on that? So once you set it up, you just need to evaluate it. So here I have y squared over 2 minus 125 y to the minus 1 over minus 1. So if I clean this up, I have y squared over 2 plus 125 over y. Plug in 10 minus plug in 5. So this gives me 10 squared over 2 plus 125 over 10 minus 5 squared over 2 plus 125 over 5. So this gives me 50 plus 12.5 minus 25 over 2 plus 125 over 5, which would be, thank you, 25. So 25 over 2 would be 12.5, so this would be 50 plus 25, so that'd be 75. Would everyone agree with that? Question?
Wouldn't the entire second equation be negative? Wouldn't it be a negative 25?
It would be, thank you, thank you. Right, because this would be 50 plus 12.5 minus 12.5 minus 25. So this would just be 25. Thank you, that was a good catch.
So you went from your bounds. How did you get those again?
That's kind of the most important thing. So I need to find, I'm integrating along the y-axis. I'm taking slices dy, because my slices, my differential is dy. So I need to make sure my bounds are on my y-axis. And I know 10 was given. Let me go back here.
Why do you have two? Why do you slice yours in the middle if you're looking for the top one?
I'm not integrating with respect to the x-axis anymore, where I go top minus bottom. I'm integrating with the y-axis, where I go outside minus inside.
So
My
that other
slices
line, the other line you
are
drew.
perpendicular to the y-axis. This is a slice. It's perpendicular to the y-axis.
I think she's wondering the significance of it, like what it
So,
shows.
okay, so this, would you agree that if I add up rectangles from this point to this point, I'm going to get the same thing as if I add up rectangles from this point to this point? It doesn't matter how I rotate it. I'm going to get the same area. Does anyone have a TI-89 or a graphing calculator that can do one of rolls? 84? You have 189? Okay, so pull it out real quick. So let's look at what we're going to do. If I wanted to integrate this with respect to x, with respect to the x-axis, I did this by hand in the other class and it took forever. So that's why I can show you. So this is the equation x equals 125 divided by y squared, right? I can rewrite that as y equals the square root of 125 over x. Do you guys see what I did there? I just solved for y. This is what I'm talking about. This is a function in terms of y. This is a function in terms of x. This point we're given y is 10. So if I plug in 10 here, I would have 125 divided by 10, and that would give me my x point. So this point here, I would have 1.25. 125 divided by 100, right? 125 divided by 100, 1.25. So this tells me this x point would be 1.25. If I plug in 1.25 here, then I have 125 divided by 1.25. Oops, my calculator's not up. 125 divided by 1.25, and then if I take the square root of that, I get 10, which would give me my y value, which this point here would be 1.25 comma 10. Do I see that? So that's going to be my bounds on x. Here, I have this would be 10 as well, right? Because this is y equals x, I could write that as x equals y. All right? So if this point's 10, then my x point's 10. So now, if I want to find the area of this with respect to the x-axis, I'm going to have to divide this up into two intervals. So I need to find this point, which we found to be 5, right? This is x equals 5. So this is not really to scale, but do you guys see that? So if I wanted to find the area with respect to the x-axis, I'm going to integrate 1.25 to 5 of my top function. What is my top function? Y equals 10. 10 is my top function. It's a constant function, right? This goes on. It's a constant function. So I'd have 10 minus, what is my bottom function in terms of x? So I'm going to write this the square root of 125 times x to the minus 1/2. I could leave it as the square root of 125 divided by x. The square root of the quantity 125 divided by x. So I could write it like this. That's going to give me the area from 1.25 to 5. Then if I add that to 5 to 10, what is my top function? 10.
But why is it 10 if it's in terms of x? Because x is changing.
It's a constant. X is not changing here. X is constant. Y is
That's
constantly
why
10.
it's not 10x.
It's not
just
10x. It's just 10. It's a constant.
Okay.
So this top function is a constant minus the bottom function to give you this area. So here, this top function 10 minus the bottom function. What's the bottom function here?
Y equals x.
So what would it be just in terms of x? Just x, right? So 10 minus x dx. Let me see your calculator. Or are you plugging it in? Okay. So what do we want to get? Hopefully we get 25, right?
The first one I got 12.5, the second one 25 divided by 2.
So 25, right? Question?
I understand why we're slicing on this one because we're breaking it up. But on the one where, like, why are we slicing it when we use it with respect to y?
So we're always slicing. We're always slicing either dx or dy because we're adding up small rectangles, right? So we need to get the general equation of the rectangle, which would be the outside function minus the inside function, or the top function minus the bottom function for the height of that rectangle, right? And then I use calculus. Here, the outside function is always y, and the inside function is always 125 over y squared. So I don't have to break this up into separate intervals to integrate it. That's why, with respect to y, is so much more straightforward. However, if I wanted to break this up, if I wanted to force it in terms of x, I would have to break this up into two intervals. Because my top function is the same, but my bottom function changes after this point. So this is going to give me the interval, the area underneath 10 and this function. And then the integration from 5 to 10 will give me the area underneath 10 and x, right? This is just a triangle, which would be easy enough to calculate.
We did it with respect to y, like the slicing didn't really play a role.
Well, that tells me I'm slicing with respect to y. And the slicing is going to be the outside function minus the inside function.
But you don't have to find out.
You don't have to divide up the intervals.
Okay.
You don't have to break it up into multiple intervals. You're slicing both ways. If I'm slicing with respect to the x-axis, that means I'm looking for the top function in terms of x minus my bottom function in terms of x. My bounds are on the x-axis. If I'm integrating along the y-axis, then I'm looking for my outside function minus my inside function in terms of y, and my bounds are going to be on the y-axis. Does that make sense? So if I hop back over here, this is A to C, and this would be B to D. Right? So I'm integrating along the x-axis from A to C. I'm integrating along the y-axis from B to D.
So with y, it'll never like change outside from inside. The one will always be on the outside, and the other one will always be on the inside.
Well, I mean,
So you
generally, theoretically, yes. But you could also encompass where it changes in terms of y, but generally, in terms of x, it's going to be a lot easier to integrate that. So let's look on Wiley. You have two choices here. You can integrate this with respect to the x-axis. So your slices are going to go from 0 to 2, and you're going to have 2x minus x squared. Or you can integrate it along the y-axis. Your y-axis would go from 0 to 4, right? And that's going to be the square root of y, because you have to solve for y, minus y over 2. So let's just take the next minute. This has the room to do it in terms of y, and this has the room to do it in terms of x.
So in some problems, by looking at the picture, you're going to immediately know that one's going to be an easier way to solve it than the other, but this one is about the same.
It's about the same. I would agree in terms of x is going to be a little easier because you're dealing with powers of whole numbers. But in terms of y, you're dealing with a fraction as a power.
Okay.
You're gonna get the same answer. So this is number 5B. So let's just look at the difference here. We have, with respect to the x-axis, which is going to be the top function, which would be 2x, minus the bottom function, which is x squared, from 0 to 2, dx. So pretty straightforward. You plug in 2 minus 0, you get 4/3. If I want to find the integral with respect to the y-axis, I'm integrating from 0 to 4 dy of the outside function in terms of y. So I have to do one extra step and solve for this in terms of x. X equals a function of y to get the square root of y, minus, and then I have to do the same thing for the inside function. If y equals 2x, then x equals y over 2. So I have the outside function minus the inside function. Integrate that, plug in my upper bound minus my lower bound, and I get 4/3 here.
So when we're doing it in terms of y, y have to be in the function.
Correct. If you're integrating in terms of y, your integrand has to be a function of y. So if they say x equals y squared, you use y squared. If you're integrating that in terms of x, you have to solve for y by itself and have a function of x. Did you guys see both ways there? So this is an example where either way is pretty straightforward, right? So the last minute, let's look at 6.1. I slide down here. What is going to be the best approach to this function? Y, right? So I have y equals 2x minus 4. The very first thing I want to do is solve for x. Then I have a function of y. And then my bounds are going to be from minus 2 to 4, because that are my bounds on y. I'm going from y equals minus 2 to y equals 4 of this function in terms of y, so I need to solve for x, minus this function in terms of y, which would be x equals y squared minus 4. Sorry, y squared divided by 4. So you could do this one in terms of x, but you're going to have to break it up. And here would be the square root of 4x, and this would be minus the square root of 4x. So y is definitely a lot easier here, but it's not impossible to do x.
But if we look at the y squared equals 4x, it's always on top of the linear.
It's not. This is on top here. The top is always true, but the bottom is not. Here, this function is on bottom. This is not a function in terms of x. It does not pass the vertical line test. Right? So this is not a one-to-one function. It fails the vertical line test. It's not a true function. So I would have to write this as y equals the square root of 4x, or y equals minus the square root of 4x. So the top function would be the square root of 4x. The bottom function would be minus the square root of 4x.
Okay. But you wouldn't have to do that if you did it in terms of y.
You wouldn't have to do that if you did it in terms of y. You only need to solve this for x and get a function of y, solve this for x and get a function of y, and take this function of y minus this function of y from minus 2 to 4. All right, we will look at 6.2 tomorrow.